Hello, everyone. Let's work out all questions uh, for the homework of Chapter 17, Electrochemistry. All right, the first question is shown here. So the question is, which of the following statements is true concerning half cell 1, which is this one, okay, as the voltaic cell shown below discharges? Okay, so this is a typical one where we talk about this usually in textbook. This is a typical example: zinc and copper. So the zinc is more reactive than copper. So here, this is the anode. Okay, so copper side is cathode. So what you need to memorize, the anode, actually the metal is oxidized. The oxidation happens. Okay, and the cathode actually is a reduction happens. All right, so electron flows from anode to cathode. Okay, so this is the basic information you need to memorize. Now let's read the options, the choices. Zinc 2 plus decreases with time, and the chloride decreases with time. Zinc will increase because zinc is oxidized. More zinc will enter the solution to form zinc, so it should be the opposite. So it should increase. Now, second choice, you see increase. This part is correct. And then chloride increase with time. Okay, chloride is high. We have a potassium chloride in the salt bridge. So over time, there are more and more zinc cation dissolved in water. So the positive charge will accumulate in the solution here. So chloride will move into the anode side to neutralize the solution. So the chloride concentration will increase. So this is correct. So apparently zinc concentration decrease is wrong, but increase is correct. But this concentration, okay, nitrate concentration increase, so it doesn't change because the concentration here, there's no reaction and no other source of nitrates. So it doesn't change over time. So that's why the last one is also wrong. So we choose number 2. Okay, this is correct. Next question. Which of the following statements regarding Faraday's law of electrolysis, which one's false, right? I ask about false. Read the question carefully. Okay, first one, 1 ampere of current equals 1 coulomb per second. This is correct. That's a definition. Okay, so we have a equation. So charge equals current times time, and the unit for charge is a coulomb, and the unit for electric current is ampere, and that's second for time. So 1 ampere times 1 second just equals 1 coulomb. Okay, so that's basically the definition. Okay, so if we do the reverse, we got the same result. Okay, second one, 1 mole of electrons lost in oxidation is equivalent to 1 Faraday of electricity. That's true because 1 Faraday equals 1 Faraday electricity equals 1 mole of electron divided by 1 coulomb electron. So that's actually the ratio of these two units, mole and coulomb. Okay, 1 coulomb actually it includes a charge. Okay, 1 mole. So the difference between them is this, okay? And 1 coulomb equals, it should be the opposite. So this is wrong. That's why we choose this one. So 1 farad equals 96485 coulomb. Okay, for most of cases we just use we only need to keep 3 significant figures. So usually we use this number. Okay, we also call it a Faraday number. Okay, the number is Faraday number. Okay, and next one mole of electrons gained in reduction is equivalent to the 1 Faraday of electricity, which is coulomb. Okay, electricity. All right, this is correct. Last one. The Faraday is a quantitative unit of electricity. Of course, it is. Next question. Calculate delta G0 for the following reaction from its cell potential. And 1 Faraday number, so we only need to use this number. Okay, the more accurate one is this one. You can use either of them to do the calculation, but I think 3 significant figures should be good enough. All right. So first of all, we can use the table from the textbook to find the reduction potential for the reactions. But here it's not really necessary because delta G for the cell. Okay, so we can find this pair. So mercury 1, this is a +1, but 2 of them to here. And here 0 to here. This is the +3. Okay, so in the table, in the textbook, so let me show you how to find it. And yeah, so you can go to the online textbook and go to in chapter 7, there's a table actually, but it just the table itself is kind of short. If you can find it, so for example, you can find this one here, which is 0.26808, and the other one for chromium. So let me copy it to here, okay? For the mercury 1 chloride here, okay? So we got this number here. And another one, the chromium to chromium 3 plus, we can find the chromium 3 is here, so we can find it's a -0.744. So another way to find it is in the textbook here. So you see in the appendix here, so you go here, so you also can find it. But this is alphabetically ordered. It's more easily easier to find here. Okay, so I think for this table you can try to print out and use for exams. Okay, this table is allowed to use for exams. Okay, now we got the potentials. Let me just write down chromium 3 to chromium. This one, I just use abbreviation. It's make it a little easier. Okay, -0.744 volts, and mercury 1 chloride. This is mercury's dimer. Okay, so and to mercury. Okay, it's a +0.26808 volts. Okay, so apparently, so mercury 1 to mercury here is 0, right? So this is reduced, right? Reduced. So chromium to chromium 3, that's oxidized. It's oxidized. So oxidized, it must be anode, okay? Reduced, it must be cathode, okay? So then this is the cathode. The chromium is anode. Anode. Okay, and we know the potential is cell potential equals E cathode minus E anode. Okay, so we do this way. So now we plug in the values. The cathode is the mercury one, so 0.26808 minus for the anode. We got it. Then we have the value, which is 1.012 volts. Okay, we keep to the thousands. Okay, thousands here. So we have very accurate value for the cathode, but we just cut to the thousands. Okay. Well, when we have it, we can calculate the equilibrium constant. We can calculate the free energy because we know the relationship between cell potential and free energy. We know delta G 0 equals negative NFE for the cell. Okay, so number of electrons involved. So you see, chromium to chromium 3, there's 3 electrons involved. There are 2 chromium atoms, so it makes it 6. For mercury, there are 6 mercury molecules. Also, not molecule, atoms. And so mercury is reduced from +1 to 0, 1 electron received, and 6 of them. So that's also makes 6. So 6 absorbed, 6 released. Okay, so that's why we have 6. And the Faraday constant is we just got it at 96500. And E, we got it just the unit is correct. We use volts. Okay, so we don't need to write unit as long as we use a standard unit for it. Then we got the result, which is minus 586,000. We keep 3 significant figures. Joule. So if we come to kilojoules, it's minus 586 kilojoule. Okay, so this is the closest one is shown here. Okay. All right. Next one. According to the following cell notation, which species is undergoing oxidation? Okay, when we have this cell notation, basically on the left side is the anode. This is the anode. On the right side is the cathode. Okay. So the reaction, basically, if you write the reaction, so here's the zinc is oxide to form zinc 2, and manganese 2 plus is oxidized to form manganese. Oh, it's the opposite should be. Okay, I don't think this is right correctly. It should be reduced. On right side should be reduced. We should reverse, write manganese 4 oxide. So there's an error in this question. So, and 2 plus aqueous, of course, and platinum is used as the plate to transfer electricity. Okay, so then this is reduced. Okay, so since we need to reverse these 2 terms. Okay, so it is asked which species is undergoing oxidation. So zinc is oxidized. So we just circle this one. On the other side, okay, at the cathode side, the reduction happens, so nothing is oxidized. So if we write this form, okay, the column, okay, so the column means, the reaction happens, means the arrow, okay, left side is reactant, right side is the product, okay. Double column means salt bridge, okay. All right, so the order is very important. You can't write it wrong, okay, because this is a +4, okay, +4, +2 to +4, okay. Both sides, for both sides, the reactions are oxidization, so that will be wrong, okay. Next question. A table of standard electrode potential is necessary for many of the following questions. Okay, so like I said, you can use the table, appendix table X, not XL, the standard electrode. So you can use that one. So, but here, it's very easy to find potassium is the most active metal, okay, in all of them. So fluorine is the oxidant, is a strong, probably one of the strongest oxidants. We can cross it. Silver, copper, they can be reduced by zinc, right? So we can cross them. Potassium is, if we check the potentials, of course, it's the most active. So it should have the most, the least value. It should be very negative. If we write a barium, it's also very strong reducing agent, but this is the product of it, right? So it's just lose 2 electrons already, or 2 electrons already. Okay, so it's a product of reduction. Okay, so we also can cross this one. So that's why we choose potassium. But if you check the table of potential, the potential energy, okay, not energy, the potential electro potential, okay, so you can find the values. The more negative one is the most negative one is the strongest reducing agent, okay. Next question. So which of the following statements about the half cell process is true for the cell shown here? So again, we need to rotate this one with it because copper is, oh, this is correct, I'm sorry. Copper 2 is reduced to copper on the right side. So this is correct notation, cell notation. So let's read the choices. First one is the spontaneous reaction that occurs in the cell is not a redox reaction. So it occurs. So for redox reaction, okay, that means there are oxidation and reduction, but this is a battery, no matter what. If the reaction happens, okay, this is spontaneous reaction for sure, and so it must be a reduction reaction, okay. So this is wrong. Next one, cadmium 2+ is reduced. So cadmium 2, no, is a product. It's the product of oxidation. So it's not reduced because it's a product. So this is wrong. Copper 2 is reduced at anode. So copper 2 is reduced, but it is at a cathode, okay? Because reduction happens at the cathode, okay, not the anode. Anode is oxidation. So cadmium 2+ is reduced at no, there's no reduction, and it's a product of anode. Okay, so the first one here, it should be at the anode. Okay, the last one is correct because copper 2 is reduced at the cathode, which is correct. Okay, it reduced to be metal copper. Okay, metal copper. Okay. Next question. A cell, or we can call it a battery. So, yeah, question 7. Which of the following describes the net reaction that occurs in the cell? Just still the same cell notation shown here. So cadmium is oxidized to, so this is a reactant, this is a product, this is a reactant, a product here. So we combine them together. So we can find a copper 2 plus is a reactant, and a cadmium metal is a reactant product. So this is correct, okay? And because it's always 0 to 2 plus 2 plus 2, 0. So both sides, but for both sides, there are 2 electrons involved. So the coefficients are always 1, okay? So that for the others they are all wrong, okay? Next question. A table of we need a table of the potential, electro potential. So the question is a voltaic cell is constructed by immersing a strip of copper metal in 1 molar copper 2 sulfate solution and a strip of aluminum in 0.5 molar silver sulfate solution. A wire and a bridge. So this is a typical one. So and the wire and the salt bridge complete the circuit. The aluminum strip loses the mass and the concentration of aluminum ions in solution increases because aluminum is more reactive than copper. Okay, aluminum is even more reactive than zinc. So the copper electrode gains mass and the concentration of a copper ion decreases. What is the cell potential? Okay, so for this question, we need to use Nernst equation. Nernst equation. So the equation is this way. The cell potential equals to the standard cell potential minus RT over number of electron times flatted log Q. Q is the quotient for the reaction. Well, so then we need to write the equation here. So copper and the copper 2 sulfate must be the cathode. So we just do a practice. We write the cell notation. So aluminum side must be the anode. So we have aluminum, metal, and the solution is aluminum sulfate, which is 0.50 molar, okay? Then we have a salt bridge. On the other side, the copper 2 sulfate solution is 1.0 molar. The product is copper solid. Okay, so that's the cell notation. That way we can write it. So if we write the complete reaction, so aluminum is a reactant. It reacts with copper 2 sulfate, which is an aqueous solution. To form product is copper solid to precipitate and the aluminum sulfate as the product. Okay, so from this side is copper 2 to copper, so 2 electrons involved for the cathode side. For anode side, aluminum 0 to aluminum 3, so 3 electrons involved. So here's times 2, here's times 3. So we have 3 here, 2 here. So it looks like both sides we should have 6 electrons. So the N equals 6. Okay, 6 electrons involved. Then we can do the calculation. So E cell, the standard potential for the cell is so as cathode minus anode. Okay, E cathode minus E anode. Okay, so cathode is copper. So copper, we check the table, we can find it is plus 0.34. Then minus aluminum. Aluminum is negative 1. Aluminum is minus 1.662. So it's very negative. So it's a very strong producing agent. Okay, then we can have 2.002. But we only can keep to the hundreds, but we can keep it for the calculation. Okay, but we know we should only have 3 significant figures here. So, all right. And we can calculate separately. So we use the equation here. So RT over NF, we can calculate first. R is 8.314. Temperature is, because this is standard temperature, so it's 298.15 Kelvin, just 25 degrees Celsius, 6 electrons. And for Faraday constant, we use, we can use 9,600. Okay, we can have this value. Let's calculate. So here we can have 4.281 times 10 to the minus third. We can have this value first, just keep it, okay, for a while. And Q is for this reaction, it equals to, so for the solid here, we don't need to include it. So, and actually it's a concentration of the products. Actually, it's aluminum concentration. Okay, and the other side is copper 2 concentration. But we need to find it's they are coefficients. So this for copper, that's 3, right? So 3, and for silver, oh, not silver. This is aluminum. But for aluminum, that should be 2 times 2. So we need to write the net ionic equation. Then we will have, 4 aluminum 3 plus. Okay. So if we convert it to, because sulfate, this part, 3 of them, they can cancel out. So we should be able to write the net ion equation for this redox reaction, and plus 3 copper 2 aqueous, and equals to 2 aluminum. Oh, sorry, there's no 2 here. It's not 4. Okay, sorry. I shouldn't put 2 here. So just put 2 for the aluminum here. So 2 aluminum 3 plus. That's correct. Okay, and we already have 2. So plus 2. This is solid. This is aqueous. So we have 2 here. So we need to convert the balanced molecular equation to net ionic equation. So that's easier for us to do the calculation. So for aluminum, that's squared. And we can find that their concentration. For copper 2, concentration is 1.0 to a third. Okay. Aluminum, so we know 0.5 molar, this one, but we have 2 aluminum here, so its concentration is 0.50 times 2 and cubed. So this is the value. Okay, we also got it equals to 1.0. So this Q equals 1. So log Q equals log 1 equals to 0. So we can just remove this term. So we don't even need to do the calculation here. So this is not necessary to calculate. Don't waste time. So then the cell potential is equal to the standard cell potential, which is this value, but we just need to keep 200, so we got 2.00 volts. So that's why we can choose this one. It's positive. Okay. Next question. Given the following standard electrode potentials, we show here. For these two reactions, calculate the standard cell potential for the galvanic cell consisting of these reactions. Okay, it looks like oxygen is reduced to form water, right? And the carbon dioxide, the carbon here is oxidized to be, this is a oxalic acid. So this is anode because it's oxidized. This is the anode. Okay, for oxygen side is it's a cathode. Okay, so we don't need to write the equation here. We just use them to calculate because the question just asks about the standard cell potential, which equals cathode minus anode, right? So then because 1.23 minus but plus, right, 0.49, then we can have a 1.72 volts. Okay, then we have this one. Next question. Which response lists all the following reactions that are spontaneous under standard electrochemical condition? So we need to check, we need to find the reduction potential from the table L in the textbook. So for chromium, the reduction potential for chromium. So if you search the table, you can find the value for chromium. So we actually in one of the previous questions we used it, but we just checked one more time, then we can find its potential, which is minus 0.744 volts. Okay, for the iron 3 to iron 2. Okay, so iron 3, be careful. There are several potentials include iron 3 plus. It should be iron 3 plus to 2 plus. Okay, let me show you if you need to find it. So here we go to iron. So several of them. You see, there are iron 3 to iron 2. So we choose this one, not iron 2 to iron, or maybe we have a bunch of different irons. Okay, choose the correct one. Okay, so iron 2 to iron 3 is a very positive, so it's a strong oxidant. Okay, 771. So for this one, iron 3 to iron 2 is positive, right? So it's reduced. Chromium to chromium 3, it's oxidized. Iron 3 to iron 2 is reduced. So this should work because the cathode, this is cathode, this is the anode, so which is correct. Okay, for number 2, iron 2 reacts with copper, so we just need to find a copper 2's potential to copper. So we use many times, it's 0.34. So copper is reduced. So from here, it's reduced. So this is the cathode. So the previous one, so iron should be anode. So, but if we do the subtraction, so then we can have a negative value because cathode value is less than anode. So it doesn't work. Okay. The last one, lithium reactor with a hydrogen. Hydrogen is 0, so hydrogen is 0. Okay. Lithium. If we find a lithium, which is very negative, one of the most negative ones. So lithium is oxidized, which is anode, right? Hydrogen is 0, so 0 is cathode, so hydrogen is a cathode. So cathode minus anode, so 0 minus negative 3.04. So we got a positive value, so this is also correct. That's why we choose this one. Next question. Which one of the following reactions is spontaneous under standard electrochemical condition? Okay, this question is similar to the previous one. So for the first one, we need to find aluminum. We found it for aluminum. I just write it really quick. Okay, minus 1.662. Copper, we know copper is plus 0.34. So copper is reduced and aluminum is oxidized. No, aluminum is reduced. The copper is oxidized. Copper is reduced, right? So to here is reduced, 0 to 2 plus. And the silver is oxidized, and the silver is the more reducing. So this is wrong. If we do, because silver is reduced, so this should be cathode, right? So negative minus the positive, so it becomes more negative, right? So it's wrong. It doesn't work. Then we need for second one. So tin 2 plus to tin. So if we check the tin value, so we got a minus 0.1375. Hydrogen is 0. Okay, it's a standard, right? So negative 1 is, which is more negative 1 is reduced. So by a hydrogen, so it doesn't work, right? So if we do subtraction, reduced is the cathode. This is the cathode. Cathode minus 0, so still keep negative. Okay. Number 3 is mercury 2 to mercury, and so mercury 2 to mercury. Okay, there are several different mercuries, so check carefully. So it's positive 0.851. The other one is nickel 2 to nickel. So the value is minus 0.257. So nickel is oxidized. So this is the anode. So mercury 2 is reduced to mercury, right? Because positive to 2 to 0, right? So this is the cathode. Okay, positive value minus negative value, we got a more positive value. So this works. The last reaction, O2 react with hydrogen, with cadmium. So cadmium is oxidized in this reaction. So cadmium, we have its value already. Okay, cadmium is minus 0.4030. And for oxygen, you can find it's a more complicated. So you can find this one, oxygen to here. So let's find it in the table. We need to find oxygen. So oxygen plus 4 hydrogen, 4 hydrogen. So under acidic condition, plus 4 electrons to form 2 water. So that's exactly the same as the, so it's the value is 1 point, is positive. Okay. Positive 1.229. So oxygen is reduced because here is negative 2, here is 0. So oxygen is reduced. Cadmium is from 0 to plus 2, so it's oxidized. So oxygen is cathode, right? So and the cadmium is the anode. So positive value minus negative value, got a more positive value. So this one also works. So that's why you choose this one. All right. Next question. Calculate the reduction potential of the copper-2 copper electrode when copper-2 concentration is this one. So this is about concentration. So we need to use Nernst equation to calculate. So, but this is a concentration cell. So when we do the calculation, we need to write it. First of all, so we know copper-2, it's aqueous, right? And plus 2 electrons, then to form a copper solid. And we know it's a potential, standard potential 0.34 volts. Okay, the standard concentration is 1 molar. But now we have a new concentration, which is 1.0 times 10 to the minus 8 moles, molar. So the concentration decreases, so it becomes more difficult to be reduced, right? More difficult to be reduced because 1 mole is a greater concentration than this concentration. So it becomes more difficult to reduce. So if we compare to the standard one, so it's more difficult to reduce. So it becomes a stronger oxidant. So it will oxidize the other one. So this is cathode. This is the anode. Okay, so now we have 2 electrodes with the same reaction, but just different concentrations. So now we can write the equation. So we can have a copper. So this is the anode, so it's oxidized. So copper solid, this is at the anode. I just put A here, okay? And the plus copper-2 plus at the cathode, okay? And this is aqueous, and we know this is the concentration here. So 1 molar equals, we don't use equal, use arrow, okay? Then this copper in anode can be oxidized to form copper-2 plus aqueous. Its concentration is 1.0 times 10 to the minus 8 mole. So the other one, 1 molar copper-2 can be reduced to copper solid. Okay, this is the anode, this is the cathode. Okay, let me just write the C, okay. All right. Sorry, my bad. This is an anode, okay. This is cathode, okay. Anode is oxidized, cathode is reduced. Okay, we proceed here, okay. All right, then we can use Nernst equation to do the calculation. So, and E cell equals E cell standard minus RT over NF log Q. Okay, now, because of the cell here, standard cell, because the 2 anode and cathode, so the reactions are the same. Okay, when it's the oxidation, but the reactions are the same. So for same standard electro potential, okay, so this one will be 0, but for the same reaction, it will be 0. So then we can just simplify it as E cell equals minus RT NF log Q. All right, we can plug in all the values here. So equals to minus R is 8.314. Temperature 25 degrees, we'll write to 98.15. It's okay to write to 98. Then write the 2 electrons involved, right? For both sides. Yeah, that's true. And 96500, okay? And log Q. For the reaction, okay, so for the product side, we use this concentration is 1.0 times 10 to the minus 8th. Okay, this is concentration, and because the coefficient is 1, so we don't need to add any power. Okay, and on the left side is 1 molar, so we just keep 1. Then just do the calculation carefully. Then we got a 0.236 volts. Okay. Now we know E cell equals E, the standard cell should be equal to cat standard minus E anode standard. Okay, so and now we got this one. Oh, sorry, we just use this one. So it's 0.236 equals the cathode is 1 molar copper 2 solution. So it is the standard one because it's 1 molar. So we use then plus 0.34 minus this new one under standard condition, but the concentration is lower. It's anode, right? So we rearrange it, then we get E anode for this lower concentration solution. Okay, equals to 0.34 minus 0.236. Then we can have a 0.104, but volts. We keep to here, right? So it's 0.10. Okay, we can just use this one. That's why it is 0.10. All right. Next question. Calculate the cell potential for the reaction below. Okay, we see this reaction, and the concentration shown here, and the pressure for hydrogen also shown here. So this is also we need to use Nernst equation. So it's not really difficult. One for zinc, we find the zinc's potential. Its potential is minus 0.7610 0.7618 volts, and for hydrogen it's 0, right? For hydrogen, it's a standard, so it's 0 volts. So apparently zinc is oxidized from 0 to 2 plus. Hydrogen is from +1 to 0. So hydrogen reduced. So it is a cathode. This is the anode. Okay. So we can calculate E cell 0, the standard condition for everything standard condition. Then we can have a cathode minus anode is 0 minus negative 0.7618. Then we got 0.7618 volts. Okay, then we can use Nernst equation. E cell equals E cell 0 minus RT over NF log Q, right? So we plug in the values, 0.7618 minus RT divided by N. So actually RT over F can be calculated first. So we use a lot. So in textbook, we have a value for it. So RTF, because all of them constant, if the temperature is a room temperature, okay. So it equals to 0.0257, okay. 257, okay. This value, yeah, this is correct. 257. So we can just use 0. So sometimes you can see for this part, we can just write 0.0257 over n number of electrons, then times log Q for this term, okay? So we can just use 0.0257 over number of electrons involved is 2 electrons, okay? So 0 to 2, okay, only one zinc, it's 2. And the log Q. So for the product, we have zinc 2 concentration, okay, zinc 2 concentration, okay, then times the pressure of hydrogen, okay, if it's gas, we use pressure of hydrogen in the unit of atmosphere, that divided by reactants. Zinc is solid, we don't need to include it, so hydrogen is a concentration, there are coefficient 2 here, okay, so we have 2 here. All right. So for this part, if we calculate separately, so if we just calculate it, then we can have zinc is 1 molar, right? 1.00 times pressure is 1.00, also 00. Hydrogen is a lower value, so it's 1.00 times 10 to the minus 6 squared. So then we just replace these values shown here. Then we finish the calculation. Okay, 0.7618 minus 0.3549. Okay, then we have a new potential, 0.407 volts. We should be able to keep 3 significant figures. Okay. So if we just keep 2, then we can find the closest one shown here, okay? All right, so this is also about Nernst equation. Next question. Cell potential for the reaction below. Okay, this is also about Nernst equation, okay? All right, so we can find the chromium dichromate to chromium. So the equation is balanced, so it's okay for us to do the calculation directly. Okay, so the chromium here is +6, here's +3, 2 of them. So 6 to 3, gain 3 electrons and 2 chromium atoms. So that's 6 electrons in total. Okay, plus 6 electrons in total. And for bromide to bromine, so here's 0, here is -1, so it loses the 1 electron from 1 bromine atom, and 6 of them, so apparently it loses 6 electrons. So now we know n equals 6. Okay, so now we can do the calculations. First, we need to find the potential for the half reactions. All right, search chromium 2. So we can write chromium 2072 minus 2, chromium 3. I just simplified, okay? You shouldn't write this way, but when we find it here, so if we search a table, chromium, so we go to here, chromium 7 with 14 hydrogen, hydrogen 6 electrons, right, to here is a 1.232. 1.232 volts. And for bromine to bromide, so we use the same way to find it. So it's 1.087. It's also quite positive. So that means bromine is a strong oxidant, but dichromate is even stronger. Okay. So then we can calculate. This is the first one. This is a bromide is oxidized, so this is the anode. Okay. And the chromium dichromate is reduced, so this is the cathode. So the E cell 0 equals cathode minus anode, right? 1.232 minus 1.0873. Then we can have 0.1447 volts. We only can keep thousands, but we can keep more during the calculation. It's fine. All right, then we can calculate the potential for non-standard condition. Okay, E cell equals E cell 0 minus RT over NF. So we can use the value directly because the three values are constants. So under room temperature, so it is a 0.0257. Okay. Then times log Q. Okay. Log Q. Q is we can get it from the solution, from the reaction. So products. Bromine is liquid here. So bromine is pure liquid. We don't need to include it. Chromium, so it's chromium 3 plus coefficient 2 here. Water is pure liquid. We don't need to include it. For reactant side, we have dichromate 2 minus its concentration, coefficient 1. Then we have a proton concentration, it's 14. And the bromide concentration, it's 6, right? So then we plug in all the values. So Q is this one. We can calculate Q separately, right? Q is equal to this. So we plug in the values here. So chromium 3 concentration 0.150. We squared it, right? And the dichromate concentration is a 0.0010. Okay, the power is 1. For proton, it's concentrated 1.00, so it doesn't change. Even 14, so it's still 0, or still 1, not 0. Okay, bromide concentration is a 0.450, but it's 6. So the Q with the calculation it equals 2.710 times 10 to the third. Okay, so we only can keep two significant figures, but we can keep more during the calculation. So we replace it, the value here with the value we got. That equals to 0.1447 minus 57 divided by 6 electrons, right? Log 2.710 times 1/3 to third. Okay, after the calculation is done, then we have 0.1109 volts. So we just keep two significant is this one. Okay, so the answer in the original question, the answer is wrong, but I replaced with the plus 0.11 volts. Okay, this is the correct answer. All right. Next question. Okay, how many milliliter of chlorine gas can be obtained at a standard condition? Standard STP condition is 0 degrees Celsius and 1 atmosphere. That's the condition, okay? By the electrolysis of molten sodium chloride, using the current here, 0.5 ampere current for 25 minutes. So, and we know Q equals I times T, right? The current times time. It also equals NF, okay? And then is the moles of electrons. This is a Faraday number, okay? So, and we can just do the calculation, and the IT equals 0.500 ampere. We can just use A, okay? It's a abbreviation is A times time. It's 25 minutes, but we need to convert it to second, okay? So it's we know 1 minute equals 60 seconds. So when we finish the calculation here, we can just plug in this value and it got something. And actually, it equals to we got a value here. So and the number moles of electrons equals IT over F. F is a Faraday number 96,500. So then the value here, the question mark here, okay. So if we do the calculation and do the division, they got number of moles of electrons involved in this electrolysis equals to 7.772 times 10 to the minus third moles of electrons. Okay. Then we can write the equation. So for 2 sodium chloride to form 2 sodium metal plus chlorine gas. Okay. So, and in this reaction, apparently there are 2 electrons involved. Okay, 2 electrons involved. So chloride. So actually, in under the Melton condition, okay, so we can write the 2 sodium plus 2 chloride, right? So 2 chloride to form a chlorine. So it needs 2 electrons, lose 2 electrons to form it. So 2 electrons involved in this reaction. So then we will have the number of electrons is shown here, the moles. So the number of moles of chlorine is half of that, right? 2 electrons to form 1 molecule of chloride. So it's N, we got the value here divided by 2. So it's just 7.772 times 10 to the minus 3 moles. Okay, divided by 2. Then we have 3.886 times 10 to the minus 3 moles chloride. Okay. Okay, we got this number moles. Okay, then we can use a PV equals nRT, the ideal gas law, right? Then rearrange the V equals nRT over P. So we got the number moles. Use this value here, and I just use 3.886 times 10 to the minus 30 moles. This is a standard unit. We don't need to write the unit during the calculation. If we R is 0.08206. Okay, we use the atmosphere later. We should use this value. Don't use it. This is everything's for this value. If you want to use this value, it's also okay, but you should use SI units for everything. Okay, but we don't have here. Okay, the temperature at the room temperature 0 degrees Celsius, so it should be 273.15 Kelvin. The pressure is 1 atmosphere, so just 1. Okay, then you can get the result in the unit of liter. Okay, 0.0871 liter. So they convert it to milliliter. So move decimal 3 times. Okay, 3 positions, which will be 87.1 milliliter. Okay, this is the result. Okay, this is the closest one. Okay. Next question. How many minutes are required to deposit the 0.25 grams, 251 grams of cadmium metal from solution that contains cadmium 2 ions if the current is 1.38 ampere? So the reaction actually is here. So cadmium 2 plus 2 electrons to form cadmium solid. Okay, so now we know the mass of cadmium. We can convert it to moles, right? If we know the moles, also we know the number of moles of electrons required. So then we can use the equation we just used for previous question, Q equals IT equals NF, right? So now we can calculate for cadmium, its molar mass is cadmium's molar mass is 52.00 grams per mole. Okay, so the number of moles of cadmium produced equals is CD. Okay, so it's 0.251 grams divided by 52.00 grams per mole. Gram cancel out, we have moles. So we have 4.827 times 10 to the minus third moles. So that number moles of electrons will be twice as many, because for one cadmium to form, it needs 2 electrons. So it's 2 NCD, right? So we can have 8, it's 9. 9.655 times 10 to the minus third moles. Okay, so you might be able to calculate directly. So if you just times 2 here directly, if you just calculate here, so times 2 directly, don't have to go through 2 steps. But anyway, both ways good. So from here we can have time equals NF divided by I. So N is the number of electrons, just this value, okay? So we have a 9.655 times 10 to the minus third moles times Faraday constant is 96500, and divided by current. Current, if the unit is the ampere, is standard unit, so 1.38. Then we have 675 seconds. We need to convert it to minutes, divide by 60. Then we have 11.3. Keep 3 significant figures. Then we got this one. Well, again, so the original answer was wrong, so I just changed. So it's not this one. We changed to 11.3. Okay. Of course, the unit is minute. The original is half of it. Apparently, it forgot to add a number 2 here. We got 2 electrons to reduce 1 cadmium ion. Okay. All right, next question. How many coulombs of charge pass through a cell if 2.4 ampere of current are passed through the cell for 85 minutes? All right, this is an easy question. So we know Q equals IT, right? So it asks about the coulomb, right? So we know ampere, so the current, which is 2.40 ampere. For 85 minutes, 85.0 minutes, right? Minutes, we just need to convert it to seconds. So because 1 minute equals 60 seconds, okay? Then this is the exact number. So when we finish the calculation, we have a 240 coulomb. So we only need to keep it 1, 2, 3. Oh, here's also 1, 2, 3. Keep 3 significant figures. We have a 12200 coulomb. If we use scientific notation, so move decimal 1, 2, 3, 4, 4 times, okay, to here. So we have 1.22 times 10 to the 4th coulomb. So this is the answer. So we choose this one. Next question. The equilibrium constant at 25 degrees for the reaction below is this is K, equilibrium constant. What is the E0 for this reaction? All right, so we just need to get the equilibrium constant. So for here, we have two equilibrium constant. So we cannot calculate directly, but we have two equations for related to free energy. One is delta G0 equal to minus NF E cell standard. Okay, E cell standard. The other is delta G0 equal to minus RT log K. Right? So delta G are equal. So we put them together, negative, negative, we cancel out. We have NF E cell equals RT log K. Then we can have log K equals NF RT over RT, then times E0. Okay, or we put 0 on the top. Okay. If we do the other side, then we will have or the E cell equals RT NF log K. So we can just use this one first directly. Okay, so E0 cell, it just asks about this, right? Equals RT over F. It's we got this number 257 and number of electrons. So copper 0 to plus 2, so 2 electrons lost. Okay. So for nitrogen, here's a plus 5, here's a plus 3, so also 2 electrons. So this is a plus 2 electrons. So 2 electrons, then log K is available here, 1.99 times 10 to the 20th. So then you just need to finish the calculation. Then we got a value here, which is 0.6003 volts. If we keep 3 significant, we should be able to keep 3 significant because we got a 0.600 volts. Okay, so this is the closest one. Okay, and because when we do the calculation, we might use the significant figure we use might be slightly different. If, for example, if we for Faraday constant, we might use the more accurate one. All right. So next question. So use the standard reduction potential below to answer the following questions. So the question is, which of the following is the strongest reducing agent? So we just need to find the most negative one. So here, the most negative one is this one, right? So we choose this one. Okay. Next one. Actually, the last question. Use the standard reduction potential given below to calculate the standard free energy change for the reduction for the reaction. So it's the nickel 2 reduced. This is the plus 2 electrons, right? Copper is oxidized to lose 2 electrons. So copper side, this is copper 2 plus gain lose 2 electrons. So it's cathode. This is the cathode. Nickel 2 is reduced to form metal nickel, so it's anode. Okay, so then we can calculate the standard free energy change, but we need to calculate the standard cell potential, which is the cathode minus anode. So minus 0.25, it's negative, right? So we also got a negative value, pretty small value. Oh, sorry, my bad. Okay. Let me erase it. Got it wrong. Sorry. So nickel is reduced. Reduced is a cathode. Okay. Copper is oxidized, so copper is the anode. Okay, so cathode. So the cell potential is cathode minus anode. So it's minus 0.25 minus negative 0.028. Then we get a small positive value for it. Only one significant figure, unfortunately. Now we can do the calculation because we know delta G standard condition equals minus NF E potential. This is the easy calculation. Okay. So that equals 2 electrons involved, and the Farad constant 96,500, and here 0.05 volts. Oh, then we have minus 5,790 joules, that comes to kilojoules, minus 5.79 kilojoules. Okay, this is the answer. So we choose this one. All right, this is the solution for all questions for chapter 17. Okay.